Our speaker today is Dmitriy Morozov, who will be telling us about topological optimization with big steps.
Great. All right. So thanks a lot for the opportunity, for the invitation, and for accommodating the 1 hour later time than you guys usually meet. I'm glad to finally be able to give a talk. So this is a talk based on a joint work with Arnur Nigmetov, who is also at Berkeley Lab. So one sort of development that I think has been very exciting in TDA over the last 5-6 years is this development of using persistence as a loss in optimization. This is, I think, is quite exciting because up until that point, persistence has been, much of TDA has been very kind of descriptive, right? Where we compute persistence diagrams from some data, maybe we use them to train some models, but it's sort of all the tasks are downstream. And when this idea was introduced, now persistence can be used to actually modify, to reshape the data given some targets expressed in terms of persistence diagrams. And it's a little bit, I found it difficult to track who introduced this first. As far as I can tell these 3 papers were sort of where it originated. So the first one is work from a Japanese group, Gumiero, Hiroko, and Obayashi. So they sort of interpolate between different point clouds by differentiating through persistence diagrams. So they have one point cloud, another, and then they try to move one into another one. Another work is by Pulinard, Primoshkaba, and Max Ovsyannikov, where they phrase various tasks used in geometry processing and mesh processing in terms of, again, in terms of persistence diagrams. So if you want to align 2 shapes, they phrase this as here's one diagram, here's another one. We want to move it one into the other and move the mesh accordingly. With lots of other tasks like this. And in the context of machine learning, there's a paper by Chao Chen and his co-authors, Yusuf Wang there, where they use persistence as a regularizer. So they say that if you want to build a machine learning model and minimize its overfitting, then you should do the following. And overfitting really corresponds to lots of topological noise in the decision boundary between a couple of classes that you see here. And then if you say that you want to find a model that has a topologically simple decision boundary, then you can express this as a constraint in terms of persistence diagrams and optimize this. And this somehow gives you a better classifier that does less overfitting. And another area where this kind of optimization is useful is persistence simplification. So if you want to get rid of noise in your function, the function may be coming from some measurement, then you can phrase this as an optimization problem. So just to make this why is this changing? There you go. Just to make this a little bit more concrete. So the idea is that if you are given a persistence diagram, you can define a loss that prescribes where points should move. So I mentioned, for example, simplification, right? So what you can say is that if I have a persistence diagram and I have some threshold epsilon, I will say that the loss associated to this diagram, sort of the penalty, is the sum of persistences squared over all the points whose persistence is below epsilon. So in other words, all of these points, they will contribute to the loss. So if I want to minimize this function, well, this corresponds to pushing these points towards the diagonal. Or for example, the paper that I mentioned on simplifying the complexity of the decision boundary, well, that if you sort of dissect what this means, it really means that let's take all the points in the quadrant centered at 0 and push them outside of the quadrant. So push them to the nearest boundary of this quadrant, and that's your loss. And so if you use this kind of loss, this is, for example, is useful in machine learning. Now, the way that this works in all of the papers that I mentioned, and lots of other papers I didn't mention, it's a large area than just 3 papers. The idea is the following. Sort of the standard approach is the following. You're given a filtration from some simplicial complex, and I think of it as a function from some simplicial complex into R. Now, your persistence diagram, every point is really given by 2 simplices, and the value, the location of the point is really the function on sigma and the function on tau. And so if you want to move this point somewhere by some gradient g sub p, well, this really translates into changing the function value f of sigma and changing function value f of tau by the respective components of this vector. Now, depending on what f is, you can backpropagate through it and translate the goal of changing the function values on the simplices into how you would change the data itself, right? So if you, for example, the filtration is a Vittori-Strips filtration, well, then the value associated to a simplex is really the length of the longest edge in the simplex. And so if you want to increase that value, well, that really just corresponds to pushing the points opposite from each other, with the points of that longest edge opposite of each other. Similarly, if your function is, let's say, some lower star filtration, the value of the simplex, so you're working with a piecewise linear function, the value of the simplex comes from its highest vertex. And so if you want to raise that value, it just translates into pushing the value of that vertex up or down if you want to decrease it. Now, I mean, the appealing part is this is very simple, right? You could, if you can compute persistence, you can implement this. The downside is that this requires taking lots of steps and there are lots of pairing switches because, of course, these functions are very non-convex, and it's a very sort of meticulous and intricate procedure. Just maybe by example, if I have a function like this, and I'm interested in, so here's its persistence diagram, and I want to get rid of this point because it's below my noise threshold. So the gradient is pushing towards the diagonal. Well, this translates into raising this point up and lowering this point. But of course, as soon as I take a step, well, there is now another wrinkle introduced, which corresponds to another point popping out of the diagonal, and now I have to recompute and push things. So if before I was pushing this point up, now suddenly I'm fighting the process and pushing it back down, which is not what you want, right? And so you have to take lots of steps like this. There is maybe the only paper that does something that's not completely sort of exactly what I described on the previous page, is the paper on the stratified gradient sampling by the authors up there. So the idea is the following, that if you think of the filtration as really a function on Rn, where n is the number of simplices in the filtration, then the space is stratified by the permutations of the simplices, right? As long as you are in some stratum that defines the ordering on the simplices, as long as the ordering of the simplices doesn't change, the persistence pairing will not change. And so the difficulty happens as you jump from stratum to stratum. And so there, and this is actually exactly the problem, right? So if your gradient takes you, if you start somewhere where simplex tau1 has value less than tau2, and your gradient pushes you into the other stratum where tau1 is greater than tau2, and then it pushes you back and forth, you start bouncing, and that's exactly what we saw on the previous slide. You start having these oscillations where first you want to go up, then you want to go down. Momentum helps here a lot, but it's often not enough. And so the idea that they suggested, Miguel and co-authors, is that you can sample points on the nearby strata, and then you can pick direction of the steepest descent in the subgradient. So this gives you really an entire polytope of directions, and you can pick the one that will descend the fastest. And what this translates into is that by doing a little bit of local sampling, you can actually follow the stratum that you want to follow. But the thing is, all of these papers, including this paper, they treat persistence as a black box. So they say that you give me a filtration, I turn that filtration into pairing of the simplices. That tells me where to move the simplices, but that's all the information that I will use. And that, of course, is kind of limiting because persistence produces much more. Any persistence computation produces much more information than that, right? The way we compute persistence is we track cycles and chains that kill them and lots of sort of relationships like this. So the goal of this paper and this talk is to open up that black box. Now, it's difficult to do in general, so I'm going to work in a very restricted setting. So let me describe the restricted setting first. So most of the losses that we saw before, they can be rephrased as a partial matching. So if for every point P in the diagram, I have some target point Q, I can think of the loss as really just the sum of all the pairs in the matching as of Q minus P squared. I mean, you could do other things, but that's sort of to the first approximation, right? So for example, when we were talking about the simplification loss, right, where we wanted to push all the points below epsilon to the diagonal, well, I can think of it as everything that's below epsilon gets matched to the corresponding point on the diagonal. Anything that's above, so this is a partial matching, anything above epsilon is left alone, and that's equivalent to taking this loss. Well, same story you could describe for this quadrant. So I want to open this black box, but I want to take a very simple. I want to understand what happens for a very simple loss, namely when my partial matching consists of a single pair. So I have one point. It has some target that it needs to go to. So there's blue point, there is its target red point, and other points have no information given to them. And in particular, the matching loss, when you have such a single point, it's completely oblivious to what happens to other points. All it tracks is this one point in this matching. Okay, so I want to understand this case, and I want to understand it in some detail.
So Dmitry, oblivious means you don't care if the other points move.
That's right. So if you compute this loss and these points moved, the loss is the same, right? It's just not they don't come into play.
Thanks.
Other questions? This is a good point to insert a question, which is why Henry did it. Okay. Okay, so let's recap persistence computation, because we're going to talk about it. So usually, so I guess the input for us is the boundary matrix, conveniently left blank. So this is the boundary matrix of the simplicial complex, where columns and rows are ordered by our filtration. And the usual reduction computes this reduced matrix R. So it sort of adds columns from left to right to get rid of, so that all the pivots, the lowest non-zeros, are in unique rows. And you can think of this process as it also is computing a matrix decomposition. So you can compute an auxiliary matrix V that has ones on the diagonal, and that tells you what are the column operations that you have to do in matrix D in order to get the columns in matrix R. So that's going to be, R is going to be a reduced matrix, V is going to be this matrix that tells us how to go from D to R, and U is going to be its inverse. And so the way you get persistence pairing, right, is why people usually think of only matrix R, is that if you look at the lowest non-zeros, they're exactly what gives you the persistence pairing, right? So if we have this kind of landscape and we have the persistence pair between these 2 points, what this really means is that in this matrix, you will have sigma as the lowest non-zero in the column of tau, which is what we have here. But the columns of these matrices also have an interpretation of their own, right? So for example, the column of tau itself, well, it's a sum of a bunch of boundaries, so it's a cycle. It's a cycle whose highest simplex is sigma, right? So lowest in the column order, but highest in the function value. So it's really a cycle that is being created by sigma that is going to be destroyed by tau. So that's the meaning of column R. And maybe more interestingly, the column tau of V is exactly this cap, right? So it's a chain whose boundary is the cycle R given by R tau, right? So it's exactly this little cap, because it has tau as its lowest simplex. So this is what this is. And if you take its boundary, you get the cycle R tau. And you just by looking at this picture, you kind of intuitively can see that maybe this is important, because if I wanted to, for example, get rid of this persistence pair and push tau down, it's not just tau that I have to push, right? It's this entire cap that I have to bring down to the level of sigma to get rid of this persistence pair. Now, in general, one should be suspicious of these kinds of claims stated about, codimension 1 cycles. But maybe if there's only one thing you remember from this talk, it's that this is actually true in every dimension. So if you want to bring the value of tau down, and you follow the gradient descent with respect to the loss, what will happen is that you will move exactly the simplices in the column given to you by the column of tau, which is sort of this cap in this picture. But Nikki, you have
Hi, Dmitry.
Hi, Nikki.
Is it clear that there's only one cap that's in that column, and that you don't have 2 caps representing that one space as a chain?
Is it clear that there is only one cap? So, I mean, maybe it's not clear that there is only one connected component. Is that what you?
Yeah, could you have a few of those little mounds in that class?
Well, so the thing that is clear is that the boundary of this cap has to be R tau. So it has to be this cycle. So I cannot just add some random stuff elsewhere, because then this will add something else to the boundary. So it can be this cap plus, I mean, the cap itself could potentially be different. And maybe one thing that you're kind of maybe is implicit in your question, the decomposition R equals dV is not unique. So I could have chosen a different cap. So you're right that maybe that's what you're sort of referring to, is that there are many such choices of a cap that will have R tau as its boundary, but there is a unique choice that's given to you by the greedy reduction algorithm. So if you just follow the original ELZ algorithm that greedily reduces D to get R, in other words, it only does the additions that are necessary and nothing else, and that gives you a unique such cap, and it's exactly that cap that you need to move.
Thanks.
Great. Other questions?
tau will necessarily be in that cap so long as the filtration times are distinct.
That's right. So tau will be in that cap, and tau in fact will be the highest simplex in that cap. Okay, so sorry, why is this? There you go. Okay, so let's now dive a little bit into what's going on, or why this is true. So here's again, let's go over an example. So imagine that I have three simplices, tau1, tau2, tau3, with values 0, quarter, and 3/4. So if I now think of this as a point in this Rn space given by the index by the simplices, then this is really a point 0, quarter, 3/4. And suppose that my goal given to me by the singleton loss is that tau1 has to move to the value 1. So in other words, tau1 needs to move to this, somewhere here. So if you just follow the gradient of the loss, this will just tell you that, well, you should just keep pushing your point to the right, keep increasing the value of tau1. And you can do this, keep going until the value of tau1 and tau2 become equal, so they're a quarter. And then in the underlying assumption, right, this tau1 is paired with some sigma, and the singleton loss is defined by the sigma tau1 pair. So if we do this, now the question is, what happens if I move tau1 past tau2? So let's suppose that if I do this, the pairing doesn't switch. Tau1 remains paired with sigma. Well, if this happens, then there is no issue. I can just keep pushing and keep increasing the value of tau1 until it hits the value of tau3. But now, suppose that if I push tau1 past tau3, the pairing switches. So now, if tau1 is greater than tau3, then tau3 becomes paired with sigma. Well, then if I go a little bit to the right, then now I will have to go, the gradient will start pushing me up. And if I go here, it starts pushing me to the right. And so what this means is that I have to keep now pushing both tau1 and tau3 together, because whichever one of them comes first is what's paired with sigma. And so the gradient will actually, if you just follow again the gradient of this loss, it will pull me along this diagonal, and it will get me to the point 1, a quarter, and 1, which is what sort of the solution would be in this case. And so what I will say is that the critical set, so this is the notion I want to introduce, in this case is going to be the simplices tau1 and tau3. And it's these simplices that define both the stratum along which I will have to move, this diagonal, and it also defines what the final destination is going to be, namely the simplices in the critical set need to get our target value, and the other simplices will remain unchanged. So the proverbial big step in the title of this paper is that we're going to figure out how to go from here to here directly. Right, so we will figure out what the critical set is, and therefore we can just move the simplices that need to move from the get-go without having to do this sort of tracing that the gradient descent would do for you. Okay, so critical set is an important idea, so let's try this one more time. So again, now let's look at this in the filtration. We have some sigma, we have some tau. Tau is paired with sigma, that's our singleton loss. And imagine that we are trying to push tau down. So as we do this, we will encounter some simplex tau1 that immediately precedes tau. And now we're interested in what happens if we transpose them. If we transpose them and the pairing doesn't change, so tau remains paired, then tau1 does not belong to the critical set. If, on the other hand, after the transposition, tau1 becomes paired with sigma, then tau1 belongs to the critical set. So that's my definition. And now you can just incrementally, you can rinse and repeat, right? As you're dragging the whole critical set down, you can examine the next simplex tau k, and you can ask, if I transpose it with the critical set, will it become paired with sigma or not? So that's another way to think of the critical set. And so, okay, so the definition that given sigma, a set of contiguous simplices x sigma is critical if placing any one of them as either the first simplex, if we're increasing the value, or the last simplex, makes it paired with sigma. Right, so that's sort of what I talked through operationally here. It just encoded as a definition, and it's the same definition if we're working with birth, death, increasing, decreasing, and so forth. Questions about the critical set? No. Okay, great. So the critical set has a couple of sort of easy to see properties once you think about them a little bit. So one thing that is the first property is that when we add a simplex to the critical set, we don't lose any simplices, right? So you can imagine a situation that, if you added some simplex to the critical set, then some of the simplices that before would be paired with sigma would now stop being paired with sigma. So the statement is this doesn't happen. Okay, so that's one half of critical set being well defined. And the other half is that if we move a simplex past the critical set, so a simplex that's not going to enter the critical set, we don't lose any simplices from the critical set. Right. So again, as we're moving the critical set, it's well defined. So we can just once a simplex enters the critical set, it doesn't leave it. So in other words, the critical set can only grow. Okay. And so if you believe these statements, which you should, then there is a very simple algorithm, very simple, naive, and inefficient algorithm for computing this critical set. You can essentially just simulate what your gradient descent does, because your gradient descent will simply just drag the simplices one by one, or it will drag the simplex, and then when it's transposed with something else, you can determine whether that simplex should be in the critical set because the pairing switched or not. Right, and so this is this very simple algorithm. The complexity of this algorithm is m squared n, where n is the size of the simplicial complex K, and m is the number of simplices between your source and your target, right? So the potential things that could become paired with sigma. So that's not particularly efficient. And so the main result of this paper is that you can identify this critical set in linear time. And you can identify in linear time the way that I described it before, namely, if you compute this decomposition, R equals dV, or D equals RU, then if you're increasing the value of the depth, then the critical set are exactly the simplices tau I that are in the row of simplex tau in matrix U. And if you're decreasing depth, then the value of depth of tau, then the critical set are exactly the simplices in the column of tau in matrix V. So that's what I was showing on the slide where we had this red cap. So it's exactly the red cap. Yeah, and this just says the same thing in words. And the crucial thing is that you need the V and the U need to come from the greedy reduction.
We had a question here. Can I interrupt you?
Yes.
At what point can you distinguish between the minimum and maximum values of the critical sets tau?
What point can I distinguish between the minimum? Sorry, I'm not sure I understand the question.
I'm also not sure if I understand this semicolon tau in the end.
Sorry,
David, if you want to just unmute yourself and say the question yourself, that would be great. Okay, it's also not clear if David has a microphone closed and everything like this. Maybe we'll just keep it. Okay. The place seems noisy. Yeah. So maybe then we will keep the question for the very end, if that's okay.
Yeah, but it's a good question while we're discussing critical set. So I think numerically, I guess maybe I will attempt to answer. So numerically, they should, all the simplices in the critical set have the same value. That's moving along the diagonal. But combinatorially, we of course break ties in some order, and either the first simplex or the last simplex, depending on which way you're moving, is what's going to be paired with the sigma that defines the singleton node. And so I guess numerically the values are the same, so I cannot distinguish between them. But combinatorially, for the purpose of persistence computation, I always can by I just add epsilon to every simplex. I don't know if that answers the question, but that's the best I can do right now.
Yeah, thanks. I think you can continue.
Okay. Right. Okay. So the main result is that by just looking at the appropriate column or row, you will get exactly the critical set, which is exactly the simplices that have to move if you want to get to where you're going. I will not go through the proof because Teresa told me that she will use the proverbial cane to yank me off at 40 minutes after the hour. But it's from the proof, it becomes transparent from the proof why you need the greedy reduction, why there is a unique structure there. Okay, so let me then say a couple more things. So I told you so far of what to do in order to increase or decrease the depth value, right? So I said there's sigma and tau, but I described what to do with tau, which is the pair that gives you depth. But in fact, it's actually very easy to get at the birth if we switch from homology to cohomology. So we just take take the duals, the vector space duals, right? The pairing is the same. If you have sigma paired with tau in homology, you'll have sigma paired with tau in cohomology. Computationally, what this means is that we take our boundary matrix D and we take its anti-transpose, right? So we reverse the order of the rows and the columns and we transpose it, right? So in other words, we flip it along this diagonal. And now if you have this matrix D perpendicular, then you can compute the same kind of decomposition. So the same way you go from D to R equals dV, you could go to R perpendicular equals D perp times V perp. And the statement is that the fact that the pairing is the same is really just the statement that if you have the lowest non-zero in the column of tau in matrix R is in row sigma, then in matrix R perpendicular, the lowest non-zero in the column of sigma is going to be in the row of tau. So in other words, computationally, it's the same thing, but the role of birth and death switched. And before, for figuring out what things are, it's just that it's only, I mean, in the analysis, which of course I skipped, it only matters that we're trying to move columns of these matrices in order to get the result on the previous page. And so what this really means is that we're done. So if you want to change the birth value, instead of looking at V and U, you should be looking at V perpendicular and U perpendicular. And the same exact reasoning gives you what the critical sets are. So in other words, the critical set, if you're trying to increase the value of the birth simplex sigma, you should look at the column of sigma in V perp, and that's going to be your critical set. Okay, so that's.
I found the notation here a bit confusing. Can you explain a bit more? The D and D perp is really just D perp is the flipped D, but then the V and the V perp is not just you take V and flip it. For D perp you compute its V.
That's right. So I start with D perp and then I reduce it in order to get R perp and V perp. Yeah.
Okay, thanks.
Very, very good question. Yes. So D perp is just D flipped, but R perp is not R flipped and V perp is not V flipped. Yeah. Great question. Thanks. Okay. So there is a little bit more that needs to be said about faces and cofaces, namely that if we are, for example, dragging simplex tau down or the entire critical set, of course, in order for us to have a filtration, we have to move every one of the faces of those simplices as well. Otherwise, we will violate the order that the face comes before the coface, right? Now, this is not particularly difficult to do. I mean, it increases complexity from OM to ODM, where D is the dimension of the complex. But in reality, we actually don't have to do this because in practice, what happens is that you take a step. This really corresponds to updating some values in your data, right? For example, moving points around or moving function values around. And then you compute the filtration. And as you do that, the construction itself will ensure that your faces come before the cofaces. And so in a sense, you can skip this worrying about faces, cofaces by just doing only moving the critical set around. But the real reason has nothing to do with complexity, of course, is just the ease of implementation. It's easy. You don't have to do the extra work to identify who your faces and cofaces are. Okay, so now the algorithm that I'll call critical set method. Sorry. So the issue is that I described what happens for a singleton loss. So if I have one point, if I want to move it somewhere, I can identify the critical set of its death, the critical set of its birth, and I can move those simplices. So that part is unambiguous because they're in different dimension. But now suppose that I have an entire matching, which is not just a singleton loss. So I need to do something. And what I do is the following, right? So for every pair PI, QI in the matching, I take, so the pair is given to me by a pair of simplices. I identify the critical set of the birth simplex. So this is my sigma. So all the sigma j that I come either from one matrix column, from one matrix or the other, depending on which direction I'm trying to move it. I do the same for I identify the critical set for the death simplex. And now, and I just append. So for every simplex now, I have some value. So if let's say bi needed to move to bi prime, now I say that for every sigma j in the critical set B, I will just accumulate all such values. So all the bi primes, I will edit I will make a list of such targets. And now I need to do something with the list, right? Because one simplex if a simplex appears in the critical sets of a bunch of other simplices, right, one can try to move it in one direction, another one can try to move it in another direction. So we will take the maximum displacement. So whoever wants to move it the farthest, that's who's going to win. And that's what we're going to do. We're going to move the simplex as far as somebody wants to move it. Now the truth is we've tried other. This is a heuristic, of course. We've tried other heuristics, namely we've tried averaging the values in target. It doesn't really change anything. It's sort of, as long as you get this extra information, that's all you really need. But in the experiments that I'm going to show, this is the procedure that was tried. Every simplex moves as far as anybody wants to push it. Okay, so that's the algorithm, which is for combining different singleton losses together, if there are. Okay, Henry is nodding enthusiastically, which I interpret as there are no questions. Okay, okay. So the first experiment is with with what they call well group loss. So the idea is that I'm trying to push points out of a quadrant at 0, and the data set is going to be something coming from a simulation where there is some topological data, and I'm just trying to simplify some sublevel set. So the first, okay, so I should explain these plots. This is a plot that's obtained by diagram method, which is just, the naive, the traditional approach that everybody takes, where you're just moving individual simplices. And this plot is really showing a vineyard, right? Where the color shows what step in the optimization this is. So this is persistence axis. This is the step. This is persistence, and this is birth plus death. So we are trying to move points in this quadrant out of it, right? So we're trying to push it out. And maybe the things to see here is that the fact that you see these yellow points that don't reach the quadrant means that after 50 steps of this optimization, we haven't actually gotten them to where they're trying to go, right? So they haven't reached their destination. Some points move outside the quadrant. That's okay. Our loss doesn't care about. And yeah, I guess you can tell sort of relative speed by how far it is from the starting point to the end point. Here's the same procedure, but using this critical set method. I guess one thing that jumps out immediately is that all the points quite rapidly reach the quadrant boundary where they're trying to go. Some points move outside the quadrant again, as that's okay. It's also instructive to look at the loss. So this is where just looking at this function. Participant has, sorry. We're just looking at this function, but tracking it during the steps of this optimization. In blue is just the diagram loss as I described it, right? Just moving the simplices. In black and in purple is a diagram loss, but also using momentum. So in other words, we accumulate the gradients as we do this optimization. The critical set method, so in other words, this is in red, it decays much more rapidly, and we can also add momentum to it, and it improves situation a little bit here. But I mean, I guess from this, it jumps out that, we can get in 20 steps to what the best of the diagram loss takes 100 steps, is maybe the one conclusion. So another experiment is the simplification, right? So we're going to try to push all the points in the one-dimensional persistence diagram into the diagonal. And so here, I guess this projection is a little bit interesting in the sense that it shows you how quickly persistence decays. But maybe what's also interesting is that the fact that you see this yellow here means that not all points manage to get into the diagonal, right? So it's not the diagram method doesn't do a perfect job, let's say. Whereas if you use the critical set method, then, well, the yellow is on the line, everything got squished very rapidly, right? So everything decays quickly. And maybe also interestingly is if you look at the loss, which is what this projection shows you, so again, blue, black, and purple is diagram loss, so this method with various levels of momentum. Red is just vanilla critical set method, so it does better already. For some choice of this momentum, critical set is just flies, right? This is logarithmic scale, right? So it gets to as far down as you can possibly push it. But what is interesting is that as you crank up this momentum, so how much gradients you accumulate from step to step, critical set method actually starts performing poorly, which I think means that we are kind of dragging old information that is of no benefit here. Which it's always beneficial to incorporate more information in the diagram method, but to a critical set method, because it already knows the entire caps, right, that you're pushing at once. this is somehow is damaging. Let's see. So maybe one more experimental observation. So one thing that is when you're working with these kinds of optimization problems that's a little bit tedious is you have to pick the learning rate. In other words, how much you scale the gradient when you're taking these steps. So what this plot shows is as you vary the learning rate, how many steps do you have to take in order to get to some target simplification loss? Some target, yeah, that's right, some target simplification loss. So you start at 7.2 and our target is 10 to the -3. So here, I guess it's revealing, right, that you get an order of magnitude improvement going from the diagram loss to the critical set method, right? So the best one that we can get here is 57 steps down to 5 steps. But maybe what's also interesting is that the best that you get is actually with vanilla critical set, right? So you don't need momentum. You just take vanilla critical set, you crank up the learning rate, and that's the best that you can get. Whereas for the diagram loss, right, for small learning rates, the momentum helps you. But then if you increase your learning rate, then momentum starts hurting you. So you don't have to make these kinds of choices with the critical set method. Maybe it's the punchline. Okay, so I have 3 minutes, so some final thoughts. So the biggest shortcoming, so maybe it's been conspicuous in this presentation that I've been talking about the number of steps it takes rather than the time that it takes to optimize. The reason is that per step time here is different, right? So the biggest shortcoming is that in order to do this, you need to compute not only matrix R, which gives you the pairing, but also matrices V and V perpendicular, which takes more time. Now, in our experiments, what this translates into is that per step computation is about 4 times slower. So given that you take 10 times fewer steps, you still win, but it's not an order of magnitude win, it's a factor of 2 win. But here there is a kind of a glimmer of hope, I would say. There's a recent work by Johan Luo and Brad Nelson on accelerating persistent homology with warm starts. So they give a very simple algorithm to update persistence, in fact, the R equals dV decomposition, if you already know a decomposition that's nearby. So if you have a filtration, you've computed its R equals dV decomposition, and now you perturb your filtration, you can actually very quickly update and get the persistence of the updated filtration. And what's useful for us is that their algorithm needs matrix V. So in other words, for us, we get it for free, right? So they need it already, and so it's an easy thing. The trouble is that when you do the update, you don't get the same matrices V and U as you would get from the greedy reduction. It's possible to fix this, so we have some work in that direction. But what the actual time improvements are, I'm not yet ready to say. Another observation that I wanted to make is that we have some flexibility in the definition of the matching. So, for example, if we're trying to simplify all the points below epsilon, right? So the loss that I've been talking about, we don't have to push them towards the midpoint and the diagonal. In fact, there's a whole bunch of them, right? The entire edge is equidistant because of the L infinity metric. And so we could push it strictly down, so to the value BB, or to the right, to the value DD. And depending on which choice we make, we need different matrices, right? So if we're pushing strictly down, so decreasing the depth value, we only need matrix V. If we're pushing strictly to the right, we only need matrix V perpendicular. And there are, of course, situations where one matrix is preferable to another, or one matrix, the obvious example, I guess, is Ripster, right? So Ripster computes matrix V perpendicular, so there you get it for free. And so if you can express your loss in just in terms of matrix V perpendicular, then somehow you are doing much better than, it's as if you only needed to compute matrix R. All right, so final remark is that I think there's a lot more here to do, because critical set really tells you how far of a step you can take confidently. And so I think there are lots of work to be done here on tighter coupling with optimizers, adaptively choosing the learning rate, in other words, what are the safe step sizes, and also understanding this strange behavior with respect to momentum better. Okay, I'm exactly on the 40-minute mark, so no canes for me. Thank you for your time and attention.
Thank you very much. It was a particularly nice talk. Can we please all unmute ourselves so that we can get together for our speaker?
So should I, oh, thanks.
You don't need to clap. We clap for you.
No, but should we stop sharing, I guess, is my question.
Maybe for questions, it's actually useful if you still have your screen shared so that if someone asks a question for a particular slide. Okay, so does anyone already have a question? Yeah, I see Bay raising her hand.
Hey, Bay.
Hi, so I have a question over the algorithm when you're dealing with multiple pairs.
Yeah.
Do you mind sharing that slide of the pseudocode where you sum them? Yeah, right here. So I'm still a little bit confused by the fact. So I understand your algorithm for singleton loss, but here you said you are going to take the largest displacement. Wouldn't that be potentially creating some sort of conflicts?
Oh, yeah. So the entire point, right, is that different singleton losses create conflicts. That if a single simplex belongs to the caps of multiple pairs that we want to move, then one pair wants to move it to one value, another pair wants to move it to another value, right? That's the conflict. So the point is that we accumulate all such conflicts in this array target. So it's really just what every singleton loss gets to contribute a value to this target array where a simplex should go, and then we can combine them. And how to combine them is purely a heuristic. You could average the values. That's a perfectly legitimate thing. You could. The thing that we do is we look at what is the largest value, sort of. What is the value that takes us the farthest away, and that's the value that we keep. But there are lots of other. I mean, it doesn't seem to make a huge difference which one you choose, but maybe that's an artifact of experiments that we've tried.
But if you do this, wouldn't that mean that you don't really resolve those conflicts? You just say, I throw
my hands up in the air and I say, I will do my best. And my best happens to be the largest displacement in this case. And it seems to work, as the experiments show, but I have absolutely no proofs about anything here.
I mean, I guess let me make a little bit more specific of, so you're saying that when you're thinking about those sort of gradient and morphing the underlying function, I saw there's an underlying assumption you want to preserve the function to be a well-behaved function somehow. But if you do this and allow all those choice of functional displacement, you don't really guarantee towards the end you have a really well-behaved function at all.
Well, let's see. I mean, so it depends on what your function is, but you can imagine if your function comes from like it's a Viatorius strips complex, right? Mm-hmm. Then each one of these values really tells you what we were discussing earlier, right? It just tells you that, okay, if this simplex wants to move here, well, this means that I will look at the longest edge of the simplex and I will move its vertices. It will just give me a little gradient, right, on each one of those vertices, and I will take a little step. And in fact, a bunch of different simplices will tell me different values for this gradient, and I will average them, right? I mean, that's done implicitly in the backpropagation, right? And so again, when you translate it back to the data, I mean, this is just telling you that, okay, if you're thinking of a function on the grid, it's telling you increase the value at this pixel, decrease the value at this pixel, right? If you're thinking about a point cloud, it tells you push it here, push it there. If you're thinking about a neural network, right? I mean, this is doing something crazy to your weights in order to match something, right? And who knows what's happening inside the neural network. But yes, so the point is that, but again, from the point of view of the filtration, you just have, here's a simplex. I want to move it here by this much, right? And this backpropagates to the data, and then I'm just changing the data.
Okay.
Sense?
Yeah. Thanks.
Thanks.
Do we have more questions? Hiya, there's another question by David. Do you perform another heuristic method to send each of the simplex to the average of its target values, concerned with the loss?
That's right. So that we've tried. So that I think is the remark here, that if you do the averaging, then the behavior it doesn't change. I mean, the performance is the same. The more interesting thing that we tried is, you see, some simplices, they get a value because they belong to a critical set of some simplex. But some simplices, they get their value because they actually appear in this matching, right? So they're the critical simplices for which we actually have the target. So one thing that we've also tried is to force that the simplices that are critical, they will get the value that they want as critical simplices. And the ones that just happen to appear in critical sets, for them, we will use one of these heuristics. Again, the performance doesn't change, which is the good news. The reason to try such a more elaborate construction is that if you look in terms of, if you tell to the critical simplices the same value that's given to them by the loss itself, then you get exactly the same. I mean, projected on them, you get the same gradient, right? So in other words, the loss doesn't care about simplices that don't appear in this matching, and on the simplices that do appear in the matching, you get the same exact values. And so this is sort of useful for trying to reason about what this is doing. But again, the performance doesn't change. I mean, my interpretation of all of this is that it's like with momentum, right? So momentum helps a lot for diagram loss because you need to move lots of simplices at once. And if you just move one at a time, then you have to take lots of steps. Whereas here, the fact that you can figure out a whole bunch of simplices to move at once in the reasonably same direction, that already does most of the legwork for you. How you exactly average them is probably not as crucial. And it's also that, I mean, for example, with the simplification loss, you can actually prove that in some settings, this maximum displacement is the best thing you can do.
David seems to have a follow-up. Oh, sorry.
Oh, go ahead.
There was just a follow-up question by David. So what happens to the singleton losses?
What happens to the singleton losses?
I'm not sure what he means with singleton losses.
I'm not sure what he means with what happens. I mean, if this was a singleton loss, right? So if the matching was just 1 point, then we would get the exact answer, right? I mean, there's no conflicts here. We just figure something out. Yeah, but what happens? I'm not sure what the question is.
So I'll jump in with a different question if that's okay. We'll just move in a different way. So I was wondering if you could go near the second to last slide where you had some figures, maybe figures 6 and 7. Yes, yeah, go forward one more.
Oh, sorry.
Yeah, here we go, 7 and 8. So I didn't have time to parse figures 7 and 8. Could you talk through them a little bit?
Yeah, absolutely, right. So our loss is, let's push all the points in the diagram into the diagonal. So in other words, any one cycle, so this is a data set on a cube, any one cycle we want to drive its persistence to 0. So that's what this loss is, right? And so with the diagram method, what you see is, I mean, the points are going towards the diagonal, right? The purple stuff is the starting point, the yellow stuff is the ending point. So they do go towards the diagonal and they go there quite, briskly, but they don't get there in 50 steps. Or maybe this is I think this is 50 steps, yeah. So you still have something left. But this is with the diagram method. With the critical set method, I mean, they get there in 10 steps or something, and they by the 50th step, they're on the diagonal, right? And this is also what you see in the loss, right? That if you even with the vanilla critical set method, right? If you start with the sum of persistences squared on the order of whatever it is, 1 or 10 or something, right? After 100 steps, it's on the order of 10 to the minus 8, right? As opposed to the diagram loss, which is dragging its feet. So I think that's what this, and this is, of course, I mean, this is this problem of persistent sensitive simplification where we, for 0-dimensional stuff, we've known how to do this for almost 20 years now, but for 1-dimensional problems we have nothing, right? So this is the heuristic. This kind of heuristic is the best we can do.
Very cool. Thank you.
I'd have another question, namely, you say that when you're lost, you don't kind of care what the other points do. Like if they're not in that kind of forbidden region or so, then they can move around if they want. Would it in some sense be better to also control those? Have you thought in that direction at all? Or can it somehow harm that they can just move around randomly?
It really depends on your problem, right? So yeah. For simplification, if you have some threshold, it's perfectly reasonable to not just say that the points below epsilon should go into the diagonal. It's also reasonable to say that the points above epsilon should be matched to the target, which is the diagram without the points below epsilon, right? So that's a perfectly reasonable thing to do. In the problems where you're trying to simplify, for example, like this decision boundary, right? You want to get rid of noise there. Well, you don't really care what happens to other level sets. You just care about the 0th level set. So the points outside of your target region, let them move. I mean, who are we to say otherwise? Yeah. So I think it's very problem dependent. So I don't think there is a kind of a universal answer.
But thanks. Yeah, you also kind of made me realize that if I don't want them to move, I can just match them to themselves. So that's right. There's always the solution. Thanks. Okay, in the meantime, I asked David to elaborate his question more. He sent it to me as a direct question. He said, after the combining loss, how do you combine all the multiple singleton losses?
Well, that's the heuristic, right, that Bay asked me to talk through. It's the singleton loss gives you these critical sets. So for every simplex in the critical set, we record what any singleton loss prescribes in this array called target. So now, after we've gone through all the points in the matching through every singleton loss, we accumulate this array of targets, which is one singleton loss tells the simplex to go here, another one tells it to go there, and then we combine them heuristically, right? So we say that the one that has that asks for the largest displacement wins, but you could also average them, for example. Right. I mean, so everything that happens inside of this loop, that's just singleton loss construction, right? Because we fix our point in the matching.
Thank you. I think that should answer the question, and we can also have more questions in that direction after the recording. But now maybe if someone else has a question. Okay, I see no raised hands. Okay, then thank you again, and I will stop the recording here.
Thanks a lot.